In part 1 I looked at how I accurately arrange all the components on the jig to get the look I want them to have and set the steering head, engine, and rear axle plates up on the jig. I referred to that as having the X and Y coordinates for the components. It would be a fairly simple matter to measure the rear lower engine mounting and establish its height over the jig and its distance along it, and get X and Y coordinates for that. But the engine mounting bracket has to go at a particular point in space across the jig, the Z coordinate, which would be only slightly more difficult to measure. The problem is that before you can measure the point you have to be sure that the engine is correctly located on the Z axis too. The same is true for the axle plates. But because of the vagaries of manufacture, the middle is not always the center. This sounds like something the Oracle would say to Neo in a Matrix movie, but is really the key to scratch building frames. Everything in part 1 was about making the frame look right. Now we are looking at making the mechanical components work with the frame we are building. The middle is not always the center means the motorcycle parts are not necessarily symmetrical around the center line. The best example of this is probably rear wheels. We know that as long as the jig was built properly, the steering head is on the center line. At the other end of the motorcycle, the thing that should be on the center line is the middle of the rear tire. In the case of the CB750 frame, the axle plates were 9 inches apart and the center of the tire was 4.5 inches from each axle plate, so sometimes the middle is the center. For the Suzuki build, however, on the brake side of the wheel the axle plate was 102 mm from the center line of the frame, but on the drive side it was 121 mm away. In American money that's around 16 thousandths over 4 inches on the brake side and around 14 thousandths over 4 3/4 of an inch on the drive side. The gap between the axle plates needed to be 223 mm, or around 27 thousandths over 8 3/4 of an inch. On the drive side the center of the sprocket was 103 mm from the center line, which is 4 55 thousandths of an inch. You could call 4 55 thousandths, 4 1/16 of an inch and not be too far out, or you could measure it in millimeters because that's the way it was made. One is obviously more accurate than the other. To recap then, the steering head is on the center line at the right height and rake, using dimensions C and D from part 1, and the front of the axle slot is the correct distance from the steering head, dimension E, from part 1. So using the measurements for the rear wheel, the axle plates can be positioned on the jig fixture at the correct distance from the center line to put the tire in the right place. Hopefully at this point you are asking yourself how you find out the dimensions for the rear wheel spacing. Simply put, you measure them from the rear wheel. By placing a straight edge either side of the rim for preference, or the tire if you must, it's easy to measure the gap between them and establish a value for W, and by measuring from the rear of the straight edge it's relatively easy to establish a value for S, the sprocket offset. With the axle and spacers installed along with a piece of tube to act as a spacer to allow for preloading things slightly, or even the axle plates themselves, values for the axle plates from the inner face of the straight edges are easily obtained. Half of dimension W plus dimension S gives the chain offset from the center line. To make things easier as the build moves forwards, it's best to measure S to the outside face of the sprocket. Positioning the axle plates from the center line only needs to reproduce the factory dimensions if you're using the factory wheel spaces and axle. If you don't have access to machining facilities, then that is probably the best course of action. It's certainly the easiest course. Armed with the necessary dimensions, the axle plates can be attached to the jig fixture. The reason for measuring S to the outside face of the sprocket is that it's the dimension used to establish the offset of the engine sprocket from the center line and is part of the way that the Z-axis locations for the engine mounting points are established. At this point, a certain number of things start to rely on establishing a horizontal line in space and relating that to the jig bed, either by eye or by measurement, so it's important that the jig has been leveled correctly and worth checking, as by now it may have been knocked around a little. The distance between the front of the axle slot and the engine sprocket, dimension F, should also be checked. With that confirmed, a rule can be placed on top of the jig bed so it passes squarely under the engine and the graduations on the rule lined up on the center line of the jig, which for the design of jig I use means the 2-inch gap between the rails of the jig bed, then a square set on the rule and used to establish the distance from the center line of the engine sprocket. At this point it becomes clear why S is best measured to the outside face of the rear sprocket. At this point the engine sprocket is positioned the correct distance along the jig as well as the correct distance across the jig. In part 1 I mentioned chocking the engine up with small pieces of wood, but I neglected to mention the reasoning for that. Almost without fail, manufacturers put their logo on their engines, Harley being something of an exception, and almost without fail those logos are level when the engine is sitting in the frame. At the mock-up stage, by chocking the engine so the logo is level, you can be reasonably sure that the bottom of the engine will be parallel to the bottom of the frame. So having ensured that the engine logo is level and the engine sprocket is in the right place, the next thing to check is whether the engine is twisted on the jig. There are two methods for ensuring this. As a first step, an engine cover is removed to expose a machined face that is perpendicular to the crankshaft. By placing a rule across this face and using a level to check that it's horizontal, then it can be checked to see if it's parallel to the jig base either by eye or by measuring. If the rule is parallel with the jig base, then the engine has to be correctly aligned. This will often be enough to position the engine, but some more awkward engines will need a bit more support than gravity alone can offer. If this is the case, then either one of the jig fixtures intended for the purpose, or just a piece of box section tack welded to the jig face, can be positioned under the lower rear engine mount, and a couple of brackets made and welded to the box section to allow a suitably sized piece of bar stock to pass through the brackets and the mount. The brackets need to sit outside of where the frame rails are expected to go, and it needs to be borne in mind that the engine mounts in crankcases are often an overly loose fit. That should provide enough stability to take care of positioning the engine in all three planes and allow it to be used as a jig for the engine mounts on the frame. The only other things of note that occur to me are that if the intention is to revolve a frame and use it to create some plans and a permanent jig for a production run, be aware that the reason that engine mounting holes in engines are something of a loose fit is that they tend to move around a little from casting to casting, and that can mean that a seemingly identical engine won't necessarily fit in a frame that was made for that type of engine. The other thing to note is that it's common practice in drag racing to open holes out to the next size up, for instance 12mm holes out to half an inch with a half-inch mounting stud for a tighter fit. This improves the all-round stiffness of the finished chassis. Power which is tweaking the frame out of line isn't making the motorcycle go faster, nor does it help with the handling. With that in mind, my preference is to use all the mounts provided by the engine. That said, I have seen plenty of rigid frames where only the two rear and one of the front mounts were used without incurring any disasters. Normally the lower rear mount is the one that does most of the work, so I like to make it a fixed mounting. The vast majority of Japanese engines come out of the frame on the right-hand side, so quite often some of the left-hand mounts will be fixed and the right removable. I tend to make both removable if both can be seen easily with the engine in the frame, simply for the sake of the symmetry. With everything set up in the correct spatial relationship, there are two more issues to consider, which are the run of the chain and the position of the exhaust ports. As a general rule, the top of the frame is going to be a straight line from the back of the steering head to the axle plates, at least that's what most people seem to consider the most appealing. The lower rails of the frame, though, can follow several different schemes. With most four-cylinder engines, when the rails have run under the engine and bent around the crankcase and set off in the direction of the steering head, what happens as often as not is that they pass right in front of an exhaust port. This can make fitting an exhaust fiddly at best, utterly impossible at worst, and usually involves adding a bend to the down tube to alter its course enough to clear the exhaust ports, normally running between the outermost port and the innermost one on each side. Water-cooled engines, especially those with the cam chain up one side of the block, will sometimes need all four exhausts to run inside the frame rails. Aside from the problem itself not being immediately obvious, it has an effect on the rear kick-up too, as any bend introduced into the front down tube will alter the rotation of the rear kick-up in relation to the bend where the bottom rails become the down tubes. In many 70s style frames for four-cylinder engines, the rear kick-up starts close to the back of the engine. I prefer to start the rear kick-up by the rear tire, simply because it minimizes the chance of anything interfering with the chain run, which is the other issue that can raise its head. This means that if the bottom rail of the frame is to be one piece, it becomes quite involved, as there are often three bends all rotated on different planes with respect to each other. One solution to this that I've seen employed is to use a piece of box section with a depth equal to the frame rails as a frame cross member at the rear of the engine. As well as allowing for a solid point for the rear lower engine mounts, the lower rails of the frame can be made as two separate sections, sleeved and plug welded together, and the join further supported by the box section cross member, which at least takes care of the rotation between the rear kick-up and the front down tubes. While the top tube and seat rails are usually much more straightforward, checking that there is clearance to fit and remove the carburetors, and for the throttle cable to do its job is worthwhile, although this should have been clear at the mock-up stage. Sometimes it's necessary to make the top of the frame a little camelbacked, with the seat rails running at more of a downhill angle than the top tube, or even to introduce a bend a little way back from the steering head along the top tube and conceal it under the gas tank. I've been Neil, your text-to-speech AI for the day, and thank you for listening. Apparently I'm supposed to ask you to like the video and subscribe to the channel, which I got told off for not doing last time. Obviously my fault because I just read what he types, but take care of yourselves and I will see you in the next one. Probably.